So thank you so much for attending this webinar. Obviously, a very exciting day, releasing Devastate the Competition today. It's my third book in my series of books. And so what's this book about compared to the others? So Devastate the Competition I wrote because of how I've seen problems and successes with how business connects to the reliability initiatives and product design. So what does that mean, business connecting? Well, when we start out making a product, we have a specific objective within the market, a certain market share we want to go after. And through the product development process, so often that objective doesn't guide the decisions during the product development program. And we end up producing a product that doesn't match what we intended and doesn't get market the way we intended. So Devastate the Competition is a summary of my observations, my methods and tools I've created, from the past 30 years of working in product development and focusing in reliability. And I wanted to, consolidate that and, put it out there in a way that hopefully people can enjoy. Okay. So a little bit about how one part of my career that kind of led me in this path is, for those who've known me for 30 years, my early part of my career was in finite element analysis. Finite element analysis is when you do the mathematical modeling of, I'm going to cut the audio so you guys aren't hanging the ding on my side, where you do mathematical modeling to calculate structural stresses, thermal stresses, vibration, all kinds of things. And in the design process, this is obviously very valuable information to engineers, and they loved having a finite element analysis department and engineers support them, and they would pursue me. I mean, they would come by and want to get to the front of the list because they need their analysis right now, and they would try to bribe you with donuts or coffee or whatever. And then in my career, I got very interested in testing and how to use analysis and testing, which led to reliability, and I ended up being the founder of the reliability department at the company I was working at with an expert they brought in. And I suddenly experienced this very different relationship with engineering, where I was now chasing them. And the things I wanted to do that I knew were very valuable felt burdensome to them. But I knew they knew it was valuable. They knew the analysis was valuable and the testing was valuable. But why? Why was it all of a sudden where from going them chasing me to me chasing them? And I wanted an answer to this question. And pursuing that over so many years now has led me to some of the things I'm going to share with you in this book. But one interesting moment was a story that I call how I almost got punched in the face at work. I'm going to share it with you here. So having built that first reliability department and having many years there, I went on to a medical company to build a reliability department for them. And, they had reliability initiatives, but they were scattered amongst the different programs. And they were looking to consolidate it. And that's why I went there. And I was a very enthusiastic, person who wanted to create this new thing. And I didn't realize how in design reviews, as I was pushing these tools and techniques on the engineers, I was really frustrating them a lot. And there was this one very, nice and smart engineer, Kevin, and I noticed more and more Kevin was kind of being distant from me, and I was kind of very much trying to implement stuff in the product development program he was leading. And once he didn't answer my questions in a meeting, and I followed him out in the hallway, and following him out in the hallway, I was like, "What's going on, Kevin?" I basically had to chase him down, and I noticed his fists were kind of clenched when he was talking to me, and I realized like how tense he was, and I was like, "Oh, whoa! Like I'm really aggravating this person. What's going on?" And I really went and thought about it. And I was like, I really have to do this differently. I have to stop pushing these reliability tools on these engineers and really kind of listen and figure out, can I get back to the way it was with finite element analysis? And they really were able to embrace and get immediate value from this. So I totally switched my tactic, and I began to just listen in design reviews and ask how I can help with things. Now, Kevin, there was a really urgent issue. This is a medical product. In Milan, a lot of field failures, and Kevin was going out there because it was the new release to see and understand what happened. And I volunteered, and I said, "Kevin, can I go with you, just to help, just to observe, support you any way I can? I just kind of want to see what happens in the field when things fail." And he kind of reluctantly agreed, and we went out there over 7 days. It was very intense. We were doing like 12-hour days in the hospital trying to figure out what was going on and solve it. And he began to see how I really sincerely just wanted to help, and we ended up succeeding. We ended up solving the problem out there, getting the information, back to home base where they started implementing solutions. And it was this great victory that we did together. So at the end of the trip, we went out to a really fancy dinner. We're charging us to the company. We found the fanciest Italian restaurant, obviously Italian restaurant in Milan we could, and started drinking. We had some wine, and we're having a good time. And one of the things that I had been sharing with him while we were there is how I loved Monte Carlo simulation, which is where you can use random number generation. If you set up a relationship between equations with too many variables, you can use random number generation to actually solve it. And I said there's a really easy demonstration of this, which is to calculate pi 3.14. I'm like, you can actually count 3.14 by making a very simple equation, a reduction of it, and you can create a random number generator. You could throw freaking stones on the ground or whatever, and the ratio they land in the circle to the square, you can screenshot this if you want to look at it, the equation. It's super simple. You can actually calculate pi, like with very few throws. And he's like, that's ridiculous. And I was like, all right, fine. So I went to a waiter who was not happy with us already, and I asked for a bunch of extra menus, and I took my plate, and I stacked up 4 menus around it. You can see like triangles. So I had a square and a circle. And I started throwing breadcrumbs in there. And then we're counting the ratio that landed in the plate versus square. So now you have 2 drunk Americans throwing food in a nice Italian restaurant, definitely getting some looks. And the reason why we were mostly getting looks is I kept forgetting to count, because at that point we'd had a couple of classes, and I kept forgetting to count and having to start over, which was making Kevin laugh so hard he was going to fall on the floor. And so that's how, I really realized then that, hey, reliability has to switch how they approach bringing their tools in. And I really have to begin to understand and pursue further now in my career how to tie it in to the end goals, so they don't become this parallel path that is no longer contributing, whereas as Ethan said, where you make an investment early on that pays off later, and it's not this parallel thing that becomes reactive. So how can I do that? What can we change? So the tool that ultimately I believe solves this is called the R3 Blueprint, but I didn't want to just jump into it. What I wanted to do was give you kind of 5 components to it that led me to it. What were 5 of the problems and observations? So we're going to do a countdown. And the first one is, when the incentivization system, I would see leaders do with their engineers, and how the leaders were actually hurting themselves with the way they were incentivizing engineers and their priorities. Time to market pressure. That's obviously the biggest counterforce to doing thorough, robust design, is that time to market pressure, which is very important. You shouldn't ignore it. You're too late to market, you're still not going to meet your business goals. So if you ask any project manager, what are the 3 most important parts of a program, they're going to say it's time to market, time to market, time to market. And that comes right down from the top. So project managers, obviously, their success, their end of the year review, their bonus is tied to that. Engineers, they have to invent within that rush time period, which means you're not going to have time to really make a robust design. You're going to get the design done and get it out there as quick as you can, because your measurement is, did you finish developing those new technologies? And you're going to do it in a very fast way. So the rewards go out when the product gets released for the engineers, for the project managers, really for most of the team. Now, typically, companies move so fast that the teams will then move on to new programs, right? And so they've been rewarded. They're moving on to a new program. Half a year later, problems start popping up in the field. What happens? They get called back as heroes to solve the problems. These are the people that are so critical, that only people that can save us. Let's pull them back in. And they get this FaceTime with the executives and these weekly updates, and they solve the problem, and there's a banner and a cake again. So what's happened? The leaders who end up holding the bag in the end for bad products have incentivized their team twice to make unreliable products. As a reliability engineer, in that configuration, I would be designing products that are unreliable just for self-preservation. So that is one observation that really made it how clear we need to figure out a way to correctly balance the time to market pressure and designing a robust design, and make sure we're making decisions with how we balance them that reflect getting to the product that is the one we want. Obviously, the one we want isn't one that gets out to market on time, and then 6 months later, you're doing a whole nother engineering iteration of it in front of the customer. That's obviously, when you look back, not what you wanted to do. It would have been better to release 3 months later and not have that iteration. So how do we get to making decisions that way? That's the first one. The second one is what I call the sideswipe. The side swipe is this. And you've seen this happen with companies and can become a downward spiral that actually it can become the end of a company. You might have seen this as well. A company will invest millions of dollars and many years in developing an amazing new technology, something that is truly a big jump. And there's a point before and after it as far as that industry goes. And they get it to market quick because obviously the longer you're holding on to it, the more likely it is somebody else is going to discover it and make a competing version of it. So we need to protect it, the IP, and we need to get it out there quick. So you get it out there quick. And there's also kind of a sense of early adopters are accepting, are kind of inviting to, no, give it to me, even though it's not done, you know? And so if you are an established name and you have good relationships with your customers, there's a pretty good chance that you're going to feel comfortable getting it out there as you're finishing it and observing risks and saying, we'll fix that in 2.0. I've heard VPs say that to me. Oh, no, you're totally right. That's scary. We'll do that in 2.0. And this kind of idea of the security. But when you get out there and the issues start happening, that forgiveness goes away pretty quick. The early adopters, usually aren't a huge volume. And as the excitement brings it out to a bigger market, that tolerance for poor reliability goes away really fast. But now your technology's out there. Now it's easy to reverse engineer. So you can have a competitor now reverse engineer it and do just a product development program based around reliability. If you're not spending all that crazy money and time doing the R&D and you're just doing a design for reliability initiative for a technology that already exists, you can do that in a very short period of time for very short money and release the robust version of the product. And here's the worst part. You can sell it at a much lower cost point. You aren't trying to recoup $500 million of R&D. You just have to recoup whatever that design for reliability program is. And that's the side swipe. Somebody comes in and effectively takes your market. And we see that a lot. And you could say, yeah, but we have patents. Well, it's pretty hard to defend patents actually nowadays, because you can make changes that are not that dramatic that can qualify as it not violating the original patent. Not to mention, patent fights in court can take a very long time. And if one company during that time is bringing in a lot of money, with high margins on sales of each product and the other one's in debt, that unto itself can really limit your ability to defend your IP. So that's the side swipe. And the scary thing is that can become a downward spiral very quickly, because now you have to go back and scramble to invent something new to try to again get market share, and you're still rushed. And if you make the same mistakes again, you're going to be in the same position again. 2 or 3 side swipes, and you've basically just done R&D for the rest of your industry and all your competitors, and they're going to profit from it, and you're in a bad place. So I'm sure a lot of you can relate to different versions of that you've seen in your industry. Number 3, the problem with Maggie. So Maggie is an engineer who has been working for 35, 40 years, getting close to retirement. She works for Acme. So Maggie is the reason why we have the reliability pressure cycle. So as an engineer, Maggie is, always working to create a great product, but she's under a lot of pressure with that time to market, pressure, and that runs right up through her organization. But Maggie also is pretty interested in making sure her 401k is being invested well and at its peak, because she's looking at retirement soon. So she's, putting pressure on her fund managers she will swap funds if they aren't performing well. And those fund managers are going to only pick companies that have really good return. And returns aren't really meant, for somebody like her, and even a lot of funds are measured on pretty short time frames. They look at quarters and then they kind of look at performance year to year. So it's not a big time frame. And the way technology moves today, you have to advance your technology quickly. Okay, that fund value comes from the stock value. The stock value comes from how the customers feel about it. Turns out Maggie is also a customer of Acme anvils, and she has her big anvil collection. She buys them regularly. She gives them out as Christmas gifts. She has no patience for a bad anvil. She will be on Amazon writing a bad review in 15 minutes after a new anvil release, and begin to drive down that company's value. You get enough Maggies out there, and you now have a big problem. So there's this crazy pressure cycle of customers turns out to be Maggie, demanding a fast time to market, which is driving Maggie's, the engineer, having to develop products too quick, but sacrificing potentially reliability, which then means Maggie, the customer, is angry, which hurts the stock price, which then forces the fund manager to drop that company in the portfolio because Maggie, the 401k owner, has no tolerance for bad performance. So it actually turns out Maggie's a bit of a problem. And she is she is a great representation of this unbelievable reliability pressure cycle that can really be crippling. And how do you stop it? It feeds itself. So that's something else I've observed, that I think that there's good methodologies and tools and techniques that can be implemented, and I share in the book, that can help with this. Number two, what is robust? You've heard me use the robust several times. What is a robust design? Well, we have invention. This is the first transistor. It was developed in 1947. This is a picture of, I think, a replica of it. The real one does still exist. This is in a museum, I think, at Bell Labs. And what you're seeing here at the bottom, that triangle, is a germanium crystal. Do you see that squiggly line on top of it? The line that goes back and forth, that piece of metal, that's literally a paper clip. They used an actual paper clip in this, and they had to get the spring force just right in how they bent it to have it work. And they created the first transistor, which was obviously a revolution. And that is a clear delimitation in technology of a time before transistors and a time after transistors. A few years later, 7 years later, was the first transistor radio. Now, before transistors, radios were literally furniture. They were in wood oak cabinets because they were so large. They had all these vacuum tubes. Transistor radio fit in your pocket, just blew people's minds. They couldn't believe it. And it had 4 transistors in it, that's all. But a pocket radio is something that can take a significant amount of abuse for an electronic, right? You take it to the beach. You can get it wet. You obviously can't soak it. You get sand in it. You can drop it, all kinds of things. And so that transistor had to function the same, but become robust. And you can see 2 features they had here. One was an impregnated case they made of composite materials to protect it from impact. And then things like electrical connections, they put these very low corrosive, reactive, like nickel pins that were very thick and strong around the very thin lead wires that were needed for it to work, because it had a very low resistance. But what I love about this drawing is, look at that. It's exactly the same design inside. You have let me just move this. You have the paper clip there, they're calling it cat whiskers now, and you have the germanium crystal, it's flipped upside down, but it's that same invention, but it's a more robust design. Okay, so then as we go forward a few more years, and you have the Game Boy, which came out in 1989, and it used a processor called the Z80, which was created in 1974. And it had 8,500 transistors in it. This is just 20 years later, 54 to 74. And actually that Z80 processor is based on one that actually came out about 6 years earlier, which was pretty similar. So in less than 20 years, 8,500 transistors working. Now, what about robustness? How much more robust is this than that first Regency radio with 4 transistors? Well, in 1990, in Desert Storm, there was a soldier who had a Game Boy and left it in the barracks when the barracks got bombed. And fortunately, nobody was hurt, but they went back into the barracks to get their stuff, and he picked it up, flipped on the on switch, it worked fine, the buttons even worked, and he was playing Tetris again. Now, that is robust. When you think about something that started off as having to have exactly the right tension on a paper clip to work right, you basically could go up to it like that and it would break, to something that you can drop a bomb on and will continue to work, that has 8,500 units of that first thing and still work fine, that is astounding. And that is a robust product. That's the process we're going through from the point of invention to having a product that your customers can depend on. So we just want to kind of keep that in mind, is that that's what the definition of robust is to me. So one definition of reliability that I like is, it's a study and control of how variabilities affect performance, right? And variability is typically becomes a bell curve with, a natural distribution if there's just variabilities and no other factors that are changing. So if variability is what we're looking to protect against, how do we do this? Well, there's two strategies. When you have the variability in the units, manufacturing, and the variabilities in the use and environment, one way you could look at it is when the weakest units come up against the strongest stresses, that overlap is going to be the failures. So to some degree, these two bell curves, where they overlap, that's going to be the percentage of the population that's going to fail. So method number one, reduce the variability. If you pull in the standard deviation of the units, now that overlap becomes less, right? And this is why we do quality control and look to reduce anything we can in variability of the unit itself. There's a second strategy. The second strategy is to increase design margins, right? This is that kind of very, that very kind of rudimentary reliability strategy of make it 2x, 3x, 4x stronger. And now you have greater margins between the stress that can cause the failure and the feature's capability. And that will reduce the overlap as well. So those are two very fundamental strategies to use to address the fact that one of the definitions of reliability is how variability affects performance. Okay, we're down to number one of the key factors that drive what I believe are the elements that get us to where you can understand how the R3 blueprint can help us. And it's time to market. I don't like this term. I feel it is very dishonest. Time to market, the way we use it, it implies that we're done. It implies that we're done with engineering. It implies that we are ready to ramp up production without any changes. But I think that we know in honesty, that's not really the case. When we say we've gotten the market, there tends to be what I call a recovery phase. The evidence of this is that there is still a lot of money going into development, that engineers and designers project managers are not able to leave the program and go on to another one. So was that really time to market as we define it? I don't think so. So I came up with a new term, time to reliability. Time to reliability to me is really what we tend to imply with time to market. Time to reliability, you should set up some kind of metric in-house that defines it. It might be that our investment budget drops down to 10% of what it was during, when the program was running, whatever its regular burn rate was. When it gets down to 10%, that clearly means we've moved on, right? We're just doing expected continuous improvement. Or it could be headcount, or it could be all kinds of things, whatever to you believe is an honest reflection of the program, concluding to where you are moving on to another program. I think it's critical. But here's the most important part. Drucker said, if you measure something, it will improve. And it's really true. If you simply measure something, it's human. So, and it's really true. It's just human nature. If you have a kid and you ask them to jump and you're like, you jumped 11 inches, they're like, what are they going to do? They're going to go and try and jump 12 inches, right? 13 inches, just because you measured it. So that's the real benefit of the time to reliability metric, is you begin to make decisions that affect the true time to reliability. If you're making decisions that just affect your time to market, which is when you start shipping it, obviously reliability is not going to be a priority, because that recovery phase is not being considered in those decisions. You start to make different decisions and creating really amazing efficiency when you really go by the metric that you've created for time to reliability. So it begins to shorten. Because you've measured it, it begins to improve. The time to reliability still will be, if you were to measure compared to your traditional time to market, be longer. But then you actually become so efficient because you're making such smart decisions for the full, for the full game. Your time to reliability can end up becoming shorter than your time to markets you had traditionally, because you are being so efficient and you are not doing all those recovery steps you even do within a program. I'm sure if I asked right now and we unmuted everybody would talk at once and say, oh my God, yes, we do so many things in the beginning of the program that cause us to fix it 3 times later, and that's even before you release. So by measuring time to reliability, you actually can end up beating your old time to markets. And when I do assessments of teams and companies, there are specific ways to measure, for me to measure these factors and associate it to a maturity level. I actually have a description of what behaviors associate different maturity levels, and you can watch organizations go through the maturity levels and improve by applying some tools that I are in the book. And you also, I think a lot of you from my other work, have seen things you can do to help advance you through these maturity levels rather quickly. So, but it really starts with honest metrics. All right. The R3 blueprint, the big reveal. First time the world's really getting to see it in this format. People I've worked with have, been able to experience in different pieces. I know Micaiah on there. We just were talking about it again yesterday. Micaiah works for Ghost Robotics. I've been working with that team for the past year. Ghost Robotics makes quadruped dog robots that are amazing. And over the past year, I've shared with them a lot of the elements of the R3 blueprint, and I feel like it's got us to a really good place. So let's jump into.
Been very helpful, Adam. Thank you.
Yes, thank you, Micaiah. So there's 3 elements, 3 R's, right? The R3: ratio factors, robust, ready, and risk guidance. So let me share a little bit about each. So ratio factors. Ratio factors are the factors that all, when brought together in sum, affect some higher level metrics. So one example could be balancing your home budget, right? It's the different factors that relate to it can be rather complex in how they work, but we do always seem to be able to, in the end, by creating one common conversion to a converted element that helps us balance it out, right? So you might have in your home budget a balance for food, one for entertainment, one for clothes, one for vacation. And each one of these behaves very differently, but they all convert to dollars that then we can look at a high level dollar value that's our budget and make decisions. So let's say we felt, our budget, we were living a little bit beyond our budget. Well, each one of these elements has a very specific relationship. Food kind of has in the beginning an easy range to adjust. You can go from buying very expensive foods to making more things. It's not that hard. You get more basic ingredients and cook more from scratch maybe, or go to no-name brands. Relatively easy. Then you get to some point where it gets harder, where you're really trying to figure out how to get the same volume of food, calories, but reduce the dollar, right? That gets kind of difficult. And then you get to a hard limit where it doesn't make sense having a home budget if you're starving your family. Obviously, there's a level you're not going to go beneath because it defeats the entire purpose. You might have something like your home entertainment budget, and your entertainment budget might be pretty much just completely a linear transition where, at the top, you're going to Disney 3 times a year. And then you're like, all right, we're just gonna do one vacation a year. And then it might be, all right, we're gonna do more local kind of things, on weekends. And then who knows, it gets all the way to the bottom where it's like, we're just gonna watch Netflix, and have our $10 a month subscription. And you might have clothes, which should be different. It has kind of a linear gradient and then has kind of a defer, an on-off switch. So it might be that you buy clothes that are of, let's say, less, whatever, brand name. And then you might be like, you know what, let's just, not buy any more clothes for this year and defer to next year. We'll just kind of keep the clothes we have going, be a little bit out of fashion, patch a few holes, and you just defer to next year. But then you are kind of carrying a balance for that specific category that then you do have to, effectively pay back to yourself. And you might have something like vacation, which actually has a cancellation threshold. And the cancellation threshold is, you can have your vacation budget be very high. We're taking everybody to Acapulco. And, then it comes down, you're like, all right, we're just going to, stay in the United States. And then, okay, we're just going to do a road trip. But if you get to the point where you only have enough money for, let's say, plane tickets or gas, and that's it, there's no point flying somewhere and flying back. You just cancel that feature. You're just wasting money. You might as well take that airplane or gas money and defer it to entertainment and go see the movies, right? A couple times a year. So they all have these complex relationships with each other, but because in the end, they all convert to dollars, you're able to balance them out and make decisions. So the ratio factors I have for products, I feel is very much the same thing. Let's just switch some of the names. We'll switch it to cost point is one budget. How do we get to the cost point that we want? How much are we willing to negotiate? How does it work? Is it like the food one where there's an easy part, a hard part, and then there's no point in selling it at this cost point? Nobody's going to buy a $2,000 pencil, right? It doesn't make any sense. You have reliability. Maybe that's completely linear with regard to how you negotiate it with the others. You have your time to market. You have some products where you can extend time to market relatively easy. You might have others where there is a hard deadline where there's no point even selling it after this date. It's not going to work. There's no point selling concert t-shirts at the concert the day after the concert, right? That doesn't make sense. Those t-shirts have to be ready by that day. And you have features. You have what technology you're investing in and what features you want to add. A great example of this is, I believe, the Mars rover, because it really is just a toy robot as far as functionality. I mean, there really are literally kids' toys that have all the same functionality. You can't do it on Mars, but within your living room can do all the same things. So let's look at what those factors would be in comparison. So for the Mars robot itself, budget, cost point, money is no object. You want to spend $7 billion? That's fine. Do you know why? Reliability is everything. There is no point. You will waste billions of $1 billion launch if this thing goes up there and we lose communication with it. You can't have the drive system fail. Those little motors in the hubs, those can't fail because you will have wasted $1 billion rocket launch. If you say we need more money to make it more reliable, that's what's happening. Time to market, same thing. If you need more time to make it reliable and do what it needs to do, you get more time. We can extend the program. The launch doesn't have to happen next year. Mars will still be there in 2 years. It can wait. Features can be compromised, meaning that we're not going to look to incorporate amazing new technology. We want to incorporate very well established technology, that we are not doing that invention of the transistor and sending transistors of the Regency radio out there. We want to be sending that Game Boy out there, something that is very mature, which means we are going to really minimize invention. So if somebody wanted to say, hey, let's invent this and put it on, that is going to be a hell of a negotiation path, because we are more than happy to exclude a feature and have this work reliably. Okay, the home science kit. Cost point, this thing better be cheap, man. This is parents buying it for Christmas for their kids. There's board games they could buy instead. So this thing can't get too expensive, and there's definitely a hard limit. If this thing gets over, let's say, 150 bucks, forget it, you're dead. No parent is going to impulse buy this one little kit while they're walking through the toy aisle, and they could also buy a million other things. Reliability, are you kidding me? This kid's going to play with it for 2 days, put it in their closet, and forget about it. And nobody's going to bring it back if it breaks. Or reliability really is not something you can have a lot of weight to negotiate with on this, that it has to work perfectly 6 months later. It really isn't going to affect sales, or even the customer probably won't even notice, because the customers at that point moved on to 4 other novel things. Time to market, this is serious. This can't be negotiated. If this thing's not on the shelves by Thanksgiving, forget it. You can't bring, our biggest sales rush is the holidays. It's the Hanukkah and Christmas and every other holiday celebrated at the end of the year. If this thing in November is not out there to be bought, forget it. Everyone's filled up most of their Christmas list by then. So that's not very negotiable. That has a real hard limit. Features, we don't have to get too fancy with this. You could try to have 1 or 2 things you invent and add that maybe, you can advertise on the box. But again, let's not get crazy, because you're not going to be able to go against cost point as far as negotiation. So 2 products that are very similar, but if you break it down by the factors, dramatically different. And these ratios are a big deal. And that is the first part of R3, is identifying these, figuring out a common element to relate them to each other, so you can make very intelligent decisions in these negotiations. Because if you don't break it down like this and have it quantifiable, these debates become really almost emotional, right? And they become very detached from really what was the original balance you had here when you decided to go after a market, and how you end up making something that doesn't fit it, is because these factors are not driving the decisions during the program. But if you don't define them, and you don't set them, and you don't show how they relate to each other, they can't guide you. I'll just take a moment. Does anybody have any questions or any comments on that, on the ratio factors?
Well, your 2 applications, your home science kit and your going to Mars, it's really the definition of what success is. And those ratios, you balance those ratios to target the success that you're looking for.
Yeah, that's actually really interesting to define. I didn't mention that really, and I kind of should include that in the description. It's a good point, Dan, is what is success, right? So success for the Mars rover is going to be some goal of providing sensory feedback for a year or 2 years from Mars. That's going to be the goal. That's success. I think success for the toy robot is getting it sold, right? Like really, it's getting it it's getting it in the kids' hands. After that, whatever, right? Like, there's so much going on there that if it breaks 4 weeks later, like I don't even know if anybody cares, right? So I think that is a really interesting point, is what is success and how different it is for these two things. Thank you, Dan. All right, the second one is robust ready. For this one, I have a broken robot, and that's because it is all about breaking stuff. So robust ready comes about because over and over and over again, I've spent a tremendous amount of energy convincing executives to not measure reliability. Strange to hear a reliability engineer say that, but I will say it again. I spend so much energy trying to get executives not to measure reliability. It is very, very harmful early in a program. So after we design something, the first impulse is, well, how reliable is it? Of course it is, right? You designed it, the transistor worked with the paper clips. How reliable is it? Well, I can save you a lot of money and time and tell you its reliability is crap. It's a freaking prototype. You just got it to work. You have 2 of them. It's not good. So there you go. You don't have to waste time and money measuring. Now, it's not just waste. It's actually hurting the program by measuring it, because you only have so much resource, money, people, time. You should be improving reliability, and that takes resource. When you have directed a lot of that resource to measuring reliability, that's resource that's not improving reliability. So you are spending all your time measuring poor reliability rather than improving it. And it's okay to improve it blindly. So what you want in your program is to have your robots always in the doctor's office waiting room. You want to be breaking your product every way possible. And this is hard because if leadership doesn't understand this, they become very frustrated. What they believe they want to see is your product working perfectly. They don't want to see it broken. But the thing is, if you're testing it to pass and not testing to fail, somehow you magically pass tests, right? That's just human nature. When you want to pass a test, you aren't going to put the hardest use case on. You aren't going to put the high stresses. You're going to excuse a lot of failures. Oh, that was a one-off. That was a whatever, right? To try to get, just for self-preservation. Leadership is, you don't want to be the one saying, hey, my part of the design keeps breaking. That's all because leadership gets very stuck on the test to pass. The robust ready principle, and I want you all to tell your leadership this, the robust ready principle is, if your leadership doesn't see your product breaking like every day, they should be highly suspicious that the engineers aren't working, because they should be doing tests to break it, because seeing those breaks and failures and root causing them, that's how you improve it. That's the fruit. That's the energy. That's the input. So the engineers can improve the design. And you need to get from that single transistor to that 4 transistor Regency radio fast. Back then they had 7 years. You don't get 7 years anymore. Are you kidding me? When there's a new invention, you better have that thing out there in 2 years. So if you don't spend those 2 years breaking it every way possible so you can make a better design, good luck. Because wasting that energy on measuring something that in the end, you're either going to measure as good as a lie, or you're going to measure as bad, and we already could have told you that, is very unfortunate. So the robust ready principle is the second principle in the R3 blueprint. And if you can't get leadership to understand it, it's going to be very hard to exercise. But they understand it. I'll say it again. If they get concerned when they don't see it broken every day. So you want your robots in that hospital waiting room constantly. Okay, the third principle, risk guidance. So this is after robust ready, and I see a hand up. Yes, Ethan.
Hi, Adam. Thank you so much. This is incredible so far. I'm just excited to be here. Question about robust ready. When you say break it, are you specifically thinking about break it in real life, or do you consider breaking it in simulation, breaking it in modeling equally valuable, even though that's not as visible and not as sort of in your face as breaking it in real life?
Yeah, so that's fantastic. And you're actually kind of hitting on that early part of my career, the progression, right? Where I did everything by analysis, right? Early on, finite element analysis, and then realized how you had to connect it with testing and, and statistics and real measurements. And the reason is those two together is the most powerful. Now, knowing when to do each and which way to let dominate a given point comes from those two expertise and deciding. So there's no generic answer. The answer is, look at how you're going to improve the design quickest by doing what. So for example, if we only have 2 prototype units and every time we break it, it's going to take weeks to fix it, but yet we know most of the breaks are in metallurgy and fatigue, geez, and you have CAD models, do tons of FEA on the structural, do as many iterations as you can, as fast as you can there. And then when you get to one that you think is like, all right, we need to anchor this again in reality, because the risk always with the finite element analysis is the boundary conditions are coming from you. It's your assumptions based on your observations. And there's always going to be a risk of your disconnect with reality. So what you want to do is this kind of pendulum swing where you do the analysis and a lot of fast iterations and design changes and explore, get to a point where you think you've optimized it, but now anchor it to reality by doing a test with something that indicates if those changes you've made are verified.
I have a quick follow-up. This is now as an executive. If there's a software heavy project, right, what should I be looking for in terms of understanding how it's breaking?
Yep. Software is really interesting because it is so different. And this is going to sound strange. Software reliability to me, strangely enough, is not about testing the software. It's about, what I do first is I analyze the practices used in making the software. Because software, those variability, remember those 2 overlapping bell curves, there's no variability in manufacturing, right? There is no real variability in the environment. It's variability of inputs going into it. And the combinations are infinite, which is where the challenge is. So what you want to do is look to the expertise from history of different practices that have been put in place in software development that when used in development, minimize dramatically the risk in these different areas. So for example, if I was an executive, I would either through my having in the past been a software person or my software experts be like, I want you to go through with me the different things you've done in design and development and show me how each one reduces risk by a known quantitative measure. I'll give you an example. If you think about where software fails, quite often it's getting a combination of inputs you didn't have before that causes an output that you didn't expect. So one thing you can do is you can go through and there's different debugging code that will go through and look for the frequency different lines of code are used in different combinations. So it then finds ones that are used very infrequently or not at all and analyzes those or removes them or finds a way to investigate that. So that practice of going through and looking for lines of code that aren't used very frequently, which effectively could be little landmines waiting out there for you with enough time added and enough people using it, you go through and address them directly. So I would be interested as an executive going through and looking and doing basically a audit of the practices done, known as best practices from decades of software development, and not really so much the testing of the software. That's where I would put my energy in the robust ready principle to improve it. Thank you. Really good question. Okay, the third part of the R3 blueprint is risk guidance. So risk guidance is now as you are advancing the design, you've done the initial robust ready, and you're looking to continue to see where you need to put your engineering resource to improve the reliability. You've started to measure it at this point. How do you best direct your resources? And you do it through risk. I always look to risk analysis output to direct resource. And the reason is we have such limited time, such limited manpower, just limited dollars. We always want to make sure we're going after the critical few issues and not the trivial many. And that can be surprisingly hard to do when you just kind of take an open look at what's in front of you, because you can see issues that are very interesting or seem very relevant, but actually are not your greatest risks. And you can spend a lot of time on them. When over here, the same amount of time and energy could have dramatically brought down your failure rate. Because it happens at a much higher frequency statistically in the field, or it turns out that much less variability in a use or environment can cause it, whereas this one is critical in effect, but it takes a much bigger variability. It's less likely. So what we want to do is use risk to guide where we put our engineering and design energy. And there's tons of reliability tools for this. Obviously, testing, specific tests. I talked about those tests that measure and improve, pulling from that toolkit. But there's a lot of really good, simple kind of my 4 points of getting regular risk input. One is failure modes effects analysis. I know those kind of have a bad name, but I think done correctly are extremely efficient. I have my 9 points of effective FMEAs, Adam's 9 points. FMEAs done incorrectly is what you want your competitors to do. It beats morale and drags on and drains resource, and it's crippling. FMEA done correctly is pretty much about one of your best tools to guide what you do in a program. You have fault tree analysis to help you when you get down to specific issues and you want to break down the elements that can drive it. Technical expertise, this is design reviews and getting those technical experts to come together and share from their cumulative lifelong knowledge and passion on a specific discipline to share the risks they have together. And the FMEA facilitates this, but you also should do a better job of capturing that in design reviews. I've been in a lot of design reviews and seen incredibly valuable points made, discussions that just kind of they get mentioned and they're never talked about again. They were never documented. They aren't, then I see an FMEA at a later date and I'm like, how was that not brought up that came up in the design review? Everybody forgot about it. So that part's really about being diligent and capturing that as the experts share their thoughts. And then, the risk summaries, having a central point where all this risk comes together and can be referenced can be very powerful too, kind of a dashboard for it, because each one of these things can become a bit isolated. Sometimes with FMEAs, the people who weren't in the FMEA, they never look at the results. They never even know, they never even see a summary. Fault tree analysis is the same thing. So creating some kind of a dashboard, a way that the risk can be very evident, can be a huge part of having risk guidance work well. So there's a couple components to risk. I mean, we have likelihood of occurrence, severity, and mitigation, detectability. These are all key elements. So there's always those components of risk that we want to try to quantify and keep consistent. And the reason why this is so important is that critical few, not the trivial many. The critical few, the word critical, how do we quantify critical? So we need to make sure that we are actually not just leaving it to kind of high-level conversation, and we have ways we can measure. And these 3 I've listed are very commonly used in FMEA, the occurrence of it, the severity, and detectability. But we want to make sure that quantitative component is always there. But with that dashboard, we're able to let risk guide us, right? It's kind of like having feedback coming in a windshield in a car. There's lots of information about risk that is coming back, but it's all there visible in front of us. So that's what I mean by a dashboard or a windscreen, is that we don't want to let the scraping on the guardrail be the feedback, right? You don't want that sound of scraping and crunching to be your feedback to change your direction. You don't want the honking from oncoming traffic to be the feedback to change direction. You want to have a way to see risk and have it steer what you're doing the way these lines are on the road, so we can get our design, to market as intended and have done it as efficiently as possible. So that's the R3 blueprint, and that's really the heart of the book and those 3 methods. But I also talk about a lot of other things about innovation and how to do innovation in a much more efficient way, which is a key part of that whole thing of that time to market and having it work. So I kind of want to share a few principles I share in the book real quick here. What I'm showing you here is September 11th, 2001, the air traffic. And something very unique happened. A lot of things happened that day that were very unusual. But one thing that is of great interest here is how fast they got air traffic control, the FAA got all the planes to the ground. So it was, let's see, at 9:45 is when they made the order to get all the planes on the ground. And there were over 4,000 planes on the ground. And in the first 10 minutes, they were able to land 700. By 11:30, they'd land 3,400 planes. That is astounding. So what was the method they did that with? How did they get that amazing amount of coordination that quick? They did it by not doing anything. The FAA and the high-level leadership for flight control said, we want all the individual controllers to work together to use their best expertise and knowledge and to coordinate at the front lines of communicating with the airplanes. They realized that was their best bet at doing it then, and they said, we'll figure out an actual method for this later. We've never had to do this before. Through analysis and over many years, they realized there's no way to do it better than that. There was no better way in that situation to get all those planes to the ground than letting the individual air traffic controllers work without hierarchy, to let them be independent masters of what they're executing, to coordinate with each other, communicate freely. There was no way to beat that with a standard practice, which I think is really interesting and can show the power of bringing control down to that frontline level. And there's companies that utilize this today that's really amazing. One is Gore. Now, we all know Gore-Tex. We all know Gore Company from Gore-Tex fabric, right? It's prevalent in pretty much about anything you do outside. An absolutely amazing innovation. But I don't think you realize how much Gore innovates. They have an insane amount of products that they produce in an unlimited amount of industries that come from their innovation. Everything from your dental floss to the best guitar strings on the market, to vascular grafts, to surgical tools. The list goes on and on. They innovate quicker at a faster pace than probably 99% of the companies out there. So the question is how? And why am I bringing that up in relation to the air traffic control example? It's because of the Dunbar number. The Dunbar number is 150. So there's the answer. The Dunbar number was first published in 1993 by Robin Dunbar, who is an anthropologist. And what he calculated, because he was studying primates, and he noticed that the groups of primates that work like a tribe changed exactly in proportion to their cognitive capabilities. So the smarter the group, the smarter the individual primate, the bigger the tribe could be. And he realized what was going on was it was how many relationships between you and somebody else, and you could keep track of between people in your mind with the limitation to the size of a tribe. So in other words, I know these 150 individuals, 150, but I'm also able to keep an idea of the relationship those 150 individuals have with each other. So what he did was he did a calculation comparatively cognitively with the primates he was working and humans and our difference in intelligence, and he came up with the number of 150. Then the amazing thing happened. You look through history, that number popped up over and over and over again in military records going back 1,000 years. Once they got over 150 people, the way that those troops or platoons or whatever they called them worked, they had to change to a different kind of hierarchy to function and stay. You couldn't have just one group that was over 150. It just showed up over and over again. Even in modern day studies with social online groups, after 150, they kind of start falling apart without some kind of hierarchy. And there tends to not be hierarchy in online social groups. So that number has shown up over and over and over again with regard to how individuals can relate to each other. Somebody once asked Mr. Dunbar, well, how would you really define this number? He goes, the simplest way is it's the number of people you would not feel embarrassed about joining uninvited for a drink if you happen to bump into them in a bar. So there's only about 150 people in the world that each one of you would feel comfortable bumping into a bar and having a drink uninvited without any nervousness. I don't know if he did a study with that. It must have been fun. But so with this, with Gore and them inventing, amazingly, you could study the inventions themselves and how they came about. But you know what is much more interesting to me than that? Their parking lots. I think their key is their parking lots. Every building they have doesn't have more than 150 parking spaces. As soon as that parking lot fills up, they build another building. They don't have hierarchy. They don't have labels or titles. The CEO is the only person with a title. They let everybody there function the same way that air traffic control worked on September 11th. That everybody stays within the size and the social dynamics of a tribe. And because of that, they can innovate astoundingly fast. Now, think about those decisions you experience in product development with when you're challenged with doing more engineering to make a design more robust versus time to market. Now, think about how far removed are the forces driving those two things? Are they across different departments? Are they across huge differences in hierarchy? What if they were in the same room, so to speak, within the Dunbar number? Would they be making smarter decisions? Would you be innovating faster and getting technology that's robust to market quicker, like Gore? So I want to thank you so much for attending this book launch, very exciting book launch, Devastate the Competition, How to Take Market Share Through Robust Design. It's available on Amazon today in both hardcover and paperback, which is great. I love talking about this stuff. Don't hesitate to reach out to me by email, phone, or go to adambarrett.com and take a look at the new website and new brand. And thank you so much for attending. Are there any final questions?
Thank you, Adam, and congratulations on another book.
Thanks so much. Oh, that's great, Ethan. Thank you.